So we were just working with the combined gas law equation where P1 times V1 over N1 times T1 equals P2 times V2 over N2 times T2. And we learned when we first were introduced to this equation that this relationship is true because at time one, those values are equal to some constant value. And at time two, they're also equal to some constant value. So they're equal to each other. Well, it turns out you can solve for that constant value, and that constant value is called R, the ideal gas law equation. Now, R will change slightly based off of the units for pressure and volume and temperature, but when our pressure is in ATM, our volume is in liters, our mole is in mole, and our temperature is Kelvin, R has a constant value of 0.08206. Now, knowing that this constant value is defined by this gas law constant R, it allows us to eliminate the need for a second set of pressure, volume, moles, and temperature data. And we can rewrite this equation simply as P times V over N times T is equal to this value R. And while this version of the equation is totally true, we usually see this in another form where we have pressure times volume is equal to the moles times R times the temperature in Kelvin, or PV equals nRT. Now, one important thing I want to emphasize when using this equation is that previously you only had to make sure your temperature was in Kelvin, but it didn't matter the units of your other variables as long as they were the same on both sides of the equation. Well, when you define R as 0.08206 liters atmospheres over mole Kelvin, well, then our pressure must be in atmospheres, our volume must be in liters, our mole will be moles, and our temperature must be in Kelvin. And now you may be asking yourself, when do I use the ideal gas law, this new PV equals nRT, versus the combined gas law, which is P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. The combined gas law that we already knew is really only used for when a gas is changing its conditions, and we want to know how variables will respond to those changing conditions, where the ideal gas law is actually a lot more powerful. We don't need changing conditions. We can find in one moment in time what one of the unknown gas variables is if we know the other three. And we're also going to use the ideal gas law whenever we're doing a chemical reaction or gas stoichiometry. So we'll see that this ideal gas law is actually a lot more useful than our combined gas law in most scenarios. Try out these ideal gas law practice problems on your own, and I'll be back in a moment to show you the solutions. Whenever I get one of these problems, I try to organize what values I know at first. Now I'm asked to find the volume of a gas that is 1 mole of gas at STP. And remember, STP is when the temperature is 273 Kelvin and the atmosphere is 1 atm. I'm going to use my PV equals nRT equation, and I'm going to rearrange it to be V is equal to nRT over P. I'm going to input my values and then solve. My unit of moles cancels out from my R and my value of moles. My unit of temperature, Kelvin, cancels out from the temperature and R. My unit of pressure cancels out from pressure in the denominator and the pressure in R. And I'm left just in the unit of liters, which is a volume. And I'll end with 22.4 liters, which maybe you already knew because this is the molar volume of a gas. Because we are asking for the volume of 1 mole of gas at STP. However, if we were not at STP, the temperature would be different, the pressure would be different, and then the resulting volume would be different. But when at STP, 1 mole of any gas will equal 22.4 liters. In this second problem, I'm going to again organize my values first. I see that I have a pressure of 1.5 atm, a volume of 3.0 liters. I want to find the moles of gas. I have R always 0.08206, and we're at 300 Kelvin as the temperature. I'm going to use PV equals nRT again, but now I'm going to rearrange it to solve for N, which will be PV over RT equals N. I put in my values and I solve. Again, my work shows that I'm left with only the unit of moles, and my answer is 0.18 mole of NH3 ammonia. So again, we're going to organize our thoughts, and we're trying to find what is the temperature in Celsius of 52 grams of nitrogen gas at 25.0 liter tank with a pressure of 1.25 atm. Well, in this situation, we're not given moles directly, but we can find moles from grams with a little gram to mole conversion. So I'm going to use the molar mass of N2, which is 28.02 because it's N2, not just nitrogen, to convert grams into moles. And I'm going to find that it's going to be 1.8558, a whole bunch of other numbers in my calculator, mole of N2. I'm not going to round this yet, but I'm going to note where my significance is, and it's at 3 sig figs. Now I'm going to take my PV equals nRT equation and put it in terms of T, which will be PV over nR equals T. Input my values and solve. All my units but Kelvin cancel out, so my temperature will be in Kelvin, and that turns out to be 205 Kelvin. I'll subtract 273.15 to convert it back into Celsius, and that's going to come out to be negative 68 degrees Celsius. And for this final problem, I'm once again going to organize my information. We have a gas in a 1.53-liter container that is at 121 degrees Celsius of temperature. I'm going to have to convert that into Kelvin, just like before. The pressure of this gas is 3.2 atm, and the question asks how many grams of this substance will be. Well, grams is not in our PV equals nRT, but moles is, and we know we can do moles to grams if we know the molar mass, and we were given the chemical formula for this diborane, so it's B2H6. Since solving this problem requires me to solve for moles first, I'm going to rearrange my PV equals nRT in terms of moles. I'm then going to input my values and solve for moles. I find that there's 0.1514 mole of gas present, and then I can take that moles of gas, multiply it by its molar mass from the periodic table, which is 27.68, using the values from our periodic table, and then we can find that the grams of diborane present are 2 sig figs, 4.2 grams.